Okay. So, in the last class we are discussing first we discussed Hermitian matrices and then positive definite matrices. Hermitian matrices we have seen that they can be diagonalized, their eigenvectors corresponding to defined eigenvalues are orthogonal. In fact, they can be normalized also, so that norm square of each eigenvector is unity. Then any Hermitian matrix we showed that it can be replaced like it can be expressed as a product of three matrices T D T Hermitian, where T is a unitary matrix, or I do not know which notation used, E D E Hermitian possibly, okay, and D is a diagonal matrix consisting of the eigenvalues. Eigenvalues are always real. Further, I considered positive definite matrices. Hermitian matrices we had a motivation because we have shown that all correlation and covariance matrices are Hermitian matrices. Then we considered another class called positive definite matrices. If a positive definite matrix has to be Hermitian and it should satisfy one property that for all non-zero x vector x Hermitian R x, if R is the matrix, R x must be real and greater than 0, greater than equal to 0 if it is positive semi-definite, greater than 0 if it is positive definite. Okay. That is where we stopped. We proved that property also, that eigenvalues are, I mean for positive definite matrices eigenvalues are not only real, they are greater than 0. For positive semi-definite matrices eigenvalues are not only real, but greater than equal to 0. That is where we stopped. Okay. Now, suppose I give you a set of random variables x 1, x 2 dot 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 say x p. This set of random variables I will be calling them linearly independent if any of them cannot be written as a linear combination of the rest. Actually, this I will elaborate further when I teach linear algebra later, but what I want to say is that they form a linearly independent set if no x I can be written as a linear combination of the rest. That is, it is not that x 1 is equal to some c 1 something, some c 1 x 2 plus c 2 x 3 plus dot dot dot. Okay. You understand what I am saying, that there is no linear relation, between this, I mean this set of variables x 1 to x p. Okay. There is no linear relation, that is you cannot have x 1 as a linear combination of x 2 up to x p, that is c 2 x 2 plus c 3 x 3 plus dot 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 plus c p x p, or x 2 as a linear combination of x 1 x 3 x 4 dot 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 x p, so on and so forth. Okay. In that case, it is called a linearly independent set. One way to check whether they are linearly independent or not is you form a linear combination like this. This I will elaborate, I tell you, when I deal with vector spaces, but I am telling something beforehand. Here C 1, C 2, C p they are constants, not random variables, but x 1 up to x p they are random variable. So, this summation is a random variable. This random variable equated to 0 means 0 random variable. There is a random variable which always takes 0 value. If we form an equation like this, and if I say that the only way this can be satisfied is by taking C 1 equal to C 2 equal to dot dot equal to C p equal to 0, if that is the only possibility, only solution for this equation, because you see if you have C 1 equal to 0, C 2 equal to 0 up to C p equal to 0, left hand side is 0. But if this is the only possibility, then only they are linearly independent. Okay. I will repeat this when I discuss vector space theory, but please see why. Because suppose Suppose you have a solution where C1, C2 up to Cp they are not 0. Some of them at least are non-zero. Suppose C1 non-zero, C2 non-zero, others are 0. Then you can take C1 x1 plus C2 x2 equal to 0, which means x1 is writable as in terms of x2, isn't it? Or suppose C1 x1, C2 x2 plus C3 x3 equal to 0, where C1, C2, C3 not 0. Then x1 can be written in terms of x2, x3, so on and so forth. If suppose just one of them is non-zero, others are 0, so C1 non-zero, that means C1 x1 is 0 vector, 0 random variable, but C1 non-zero, that means x1 must be the 0 random variable. But 0 random variable, if you have 0 random variable in this set becomes linearly independent, because any 0 random variable is a linear combination of any set of variables. So, 0 x1 plus 0 x2 like that. Okay. If you have just coefficients equal to 0, so any 0 random variable if you add to the any set, that set becomes linearly dependent, because 0 random variable can be written always as a linear combination of any set of random variables. So, when there is such linear relation existing between a set of random variable, we say they are linearly related, linearly dependent, but if there is none, they are linearly independent. Now, you know, very rarely only we have situations in real life where there is a linear relation involving random variables. In practice, most of the random signals we do not have such equation, you know, governing, I mean saying that one of the random variables is a linear combination of the other. There is nothing like that. Occasionally that arises and they lead to beautiful algorithm and structures and all that. That is a separate story. Okay, that is a separate story, but otherwise not. For example, if you give a sinusoidal signal, you sample it say for 3 or 4 periods. Sinusoidal signal with amplitude A is random. So, then every time you measure sinusoidal signal, the amplitude fluctuates. So, it is a random process, random signal, because the amplitude A is changing. But the samples that we have in successive sample, I mean suppose in 3 full periods, they form a linearly dependent set, because the sample that you have in first period, that will occur again in the second period and occur again in the third period. So, if you want to represent as a linear combination of the rest of the sample, you put 0 values to all other coefficients, take 1 value to the repetition case. Okay. So, there you have got linear relation, linear dependence. But in practice, especially when you deal with real life random signals, unless there is a structure that is governing the genesis of the random process, I will tell you there are such cases which occur rarely, but they occur and they are very well defined cases and have potential applications. Except for those cases, especially for our case, we do not have situation where one random variable is say summation of some other random variables, because that will imply redundancy. Suppose x, y, 2 random variables, and you say no, x, y not enough, you take x plus y equal to z also. I say no, x and y enough, in terms of them I can have z. So, x, y, z in that case form a linearly dependent set, but not x, y, isn't it? Not x, y. So, in practice we will deal with set of random numbers or random variables which are linearly independent. There is no linear relation involving them, that is none of them expressible as a linear combination of the rest. That is what happens most of, I mean on most of the occasions. Okay. Now, let us consider a random sequence x n. Again I assume random sequence x n, okay, and you form a vector call it x n vector, in general complex valued. You find out this correlation matrix R x x, this autocorrelation matrix you all know, we have defined it. You could have taken covariance matrix also, because but whatever I am saying that is equally valid for both correlation matrix and covariance matrix, and also I will be most often dealing with zero mean variables, which means correlation covariance meaning same. No question of subtracting mu, because mu will be 0. Most often, I mean, throughout this course rather, I will be dealing with zero mean random processes. So, that is why correlation or covariance they always would mean the same, because mean will be 0 in our cases. Anyway, take a form like this. We all know RxX is Hermitian, about that there is no doubt. We have seen in the past that RxX is Hermitian. Now, so first thing is RxX Hermitian, that we know, we have seen earlier. Next, you take any vector, choose any vector, any u not equal to 0, any vector. Then if you take an u equal to, where u is equal to say u 0, u 1 dot 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 u p, u 0 to u p, okay? Take any non-zero vector. Then if I form this summation, there can be complex valued coefficients, okay? If you form the summation u h r x x u, I will show that r x x is not only Hermitian, it is positive semi-infinite, and if there is no linear relation between x n up to x n minus p, that is if they form a linearly independent set, it is not only positive semi-definite, it is actually positive definite. Positive semi-definite always, Hermitian done. Other property have to prove that for any non-zero vector u, if you take a product u Hermitian r x x u, this is a real quantity and greater than equal to 0. If I can prove that, there is positive semi-definite or equivalent equal non-negative definite. But further I will show that if there is no linear relation involving these elements of the vector, that is if the elements of the vector form a linearly independent set, there is none of them, no x n is a writable as a linear combination of the others, and that is what happens most of it, isn't it? You do not observe a random process in lab where one sample is some summation of or linear combination of the past few samples, exactly. There will be an error, but it is not an exact summation of some previous samples, isn't it? So, then this matrix is not only positive semi-definite, it is in fact positive definite, that is what we will show. Okay? And this is independent of whether x n is w set stationary or not. Okay, I am not even assuming that correlation depends only on lag and all that. So, whatever I say now, that is independent of, this is more general, that applies both to the case where x n is stationary and x n is not stationary. I am not using WSS property of x n here. Whatever I say, that is most general. Okay. Now, consider this u h r x x u, r x x you know this, u is constant, no random, there is no random variable in u, u consists of scalar constants, r x x is e of this and followed by again u. So, both u h and u can be pushed inside the expectation operation because they are constants. Isn't it? This x n is random, it consists of random variables, but not u, u consists of only constants. You know, constants can be brought inside the expectation operation. After all, expected value of 2 x is 2 into expected value of x, 2 can go out or can come in the reverse way. So, that means this is same as u, expected value u h x n and x Hermitian n u. Okay. Suppose u h x n, what is u h? A row vector. What is x n? Column vector. So, it is a scalar. And what is this? Row vector, column vector, scalar. If you call this A, my claim is this is A Hermitian, which is nothing but A star, because A is scalar. Scalar has no meaning of transposition, isn't it? You can see if you take this A, if you take the Hermitian of this, x will come first with x Hermitian, this will go as the second guy, Hermitian on Hermitian, Hermitian goes, you get back u. So, A Hermitian and A is a scalar. So, A Hermitian means A star only, no question of transposition. So, this quantity is real because mod A, so it is a real quantity, mod A square. So, non-negative quantity, expected value of mod A square can never be negative. Okay. Mod A square can never be negative. So, this is always greater than equal to 0, always. So, positive semi-definite or non-negative definite always true. When it is equal to 0, if it is equal to 0, then A should be the 0 random variable. That is, whenever you measure A, you only get 0, then only expected value of mod A square will be 0. If A is 0 random variable, that means u Hermitian x n is a 0 random variable. That is, A equal to 0 implies u Hermitian x n, that is u 1 star, sorry, u 0 star x n plus u 1 star x n minus 1 plus dot dot u p star x n minus p, that is equal to 0 random variable. This 0 is a random variable. What does it mean? You chose u as non-zero vector. That means not all the coefficients of u are 0. That is, say all, suppose the coefficients are, I mean not all the coefficients are 0. This means there is a linear relation between the elements of x n x minus 1 up to x n minus p. That is, they are linearly dependent. So, only if they are linearly dependent, I can find at least one u and therefore many u, for which this will be equal to 0. For other choice of u, it will be greater than 0. So, when they are dependent, this is indeed greater than equal to 0. But when they are not dependent, when this is this set x n up to x n minus p, they are, what I am saying is they are a linearly independent set. In that case, this can never be equal to 0, because you told me u consists of, u is a vector which is a non-zero vector. So, all the coefficients are not 0 simultaneously. You also told me that this is a linearly independent vector, that is all the elements are linearly independent, and then this summation can never be equal to 0, because that will mean they are linearly dependent. Contradiction, isn't it? That is not possible. So, that means if there is no relation, no linear relation involving the set of random variables at hand, then this quantity is actually greater than 0. Positive definite. So, in any case, a correlation matrix will have real eigenvalues which are always greater than equal to 0, but in most often when there is no linear relation involving the random variables, eigenvalues will in fact be positive, and therefore, the correlation matrix will be invariable, because after all determinant of the correlation matrix will be same as determinant of product of the eigenvalue that we have seen last time. Okay. Now, this kind of processes are called full rank processes. If you take any arbitrary number, p can be 1, p can be 2, you can take 2 samples of the random process 3 or 30 or 30,000, if there is no linear relation amongst them, if no random variable can be expressed as a linear combination of either 1 or 2 or 3 or any number of, I mean any other samples in their sequence, that is called a full rank process. For our case, if it is linearly dependent up to p is okay, where I am taking only correlation matrix up to order p. Okay. So, you understand why I was so long talking about Hermitian matrices, because correlation matrices or covariance matrices, they are not only Hermitian, they are positive semi-definite always. We have seen it here, and most often positive definite in fact, because the processes are full rank processes. Okay. So, with that I now start the basic Wiener filter or optimal filter. So long whatever we discussed, this is our background, this is our background material. Again we will develop background material afterwards, but this is the key. That is, suppose I have got a random sequence x n, 0 mean, WSS, 0 mean. So, mean is stationary of course, because mean is 0 everywhere and correlation depends only on lag. So, start with assume that is WSS, 0 mean WSS process. Okay. I want to find a filter, FIR filter, maybe with some coefficients W0 dot 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 WP. So, what is the output Yn? Yn is, you all know W0 xn, you know this, isn't it? Which is, and again I forgot to mention one thing, to make life simple, to start with we will be dealing with only real valued case. We will develop Wiener filter, then we will develop adaptive filter from this all for real value. Then again I will come back to this, I will generalize the case to complex value, because the treatment has to be different there. Two different treatments exist. So, for the complex cases things are defined in a different way. So, for the time being I am dealing with real valued cases. So, even when I use the Hermitian symbol, I simply would mean transposition, nothing else. There is no complex conjugation required, because there is nothing complex, okay, for the time being. which is same as W transpose vector x n vector. Did you understand what is W vector? I do not think I have to tell you. W vector is a column vector, W 0 to W p, x n is a column vector, x n to x n minus p. This is a filter output. Now, the filter output I want to be, but input is random means output also random. So, I want this to be a good estimate of another signal, target signal D n, some target signal. That means, what should I do? You cannot say that let y n be equal to D n, because for a particular index n, you can equate the two. You have only you can equate y n equal to D n. So, you can have one equation with so many unknowns, you find some solution, fine. But immediately the next index comes, y n will no longer be D n, there is a huge difference. So, y n equal to D n will not work. And also these things are random. D n minus y n, that is error, this is that also, that error also is random, isn't it? Only thing is, x n is stationary means y n is stationary, x n and D n they are jointly stationary. Jointly stationary means, if you take the correlation between x n and D n, again that will depend on the lag, they are jointly stationary. I write down, that is what is given is R, I am dropping R x x, just R applies for the input, E, I am writing transpose here, no point in putting Hermitian. Hermitian also will not do any harm, but still for your consumption I am doing this. And correlation matrix and covariance matrix are same here, because I am dealing with 0 mean cases. This is given, and we see this is independent of n, obviously because I assume WSS input, that is why R does not depend on n. Another thing is, it is given is cross correlation. Okay, you excuse me, instead of W 0 to W p, maybe I just switch base p, I will be using p using something else. So, instead of W 0 to W p, maybe we can make it just bring these changes. E of say x n d n minus say k. So, correlation, but not on with x with itself, between x and d, lag is k. If I say jointly stationary, then this correlation also depends only on the lag. Then the two processes are jointly stationary in the second order, that is in correlation. So, that will be then a function of k only. Okay. You can call that p, this p notation is reserved there in all books for that. That is, you have to change from p here to something else. Okay. P k, and we define the vector p as p 0, p 1 dot 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 p n, which is nothing but these are my definitions. Or maybe you can make it d n, though it will be same in this case, d n x n minus k. Okay. For the real case, you know that correlation between d n and x n minus k or x n and d n minus k, they are same. Correlation is Hermitian as such, or if it is real, correlation at a lag k and correlation at a lag minus k, they are same. Only when they are complex, there is a problem. They conjugate, not only same, they are conjugate of each other. So, I could as well keep x n here, d n minus k here, but for your consumption, for your to avoid confusion, I am changing it so that when you write E of x n into d n, you indeed get this. What is x n vector after all? First element is x n into d n p 0. Second element is x n minus 1, x n minus 1 to d n, that is p 1, x n minus 1 d n p 1 dot dot dot, that is why I change it, okay, to conform to this. But even if I had kept x n here and d n minus k, things would not have been different, because in the real case expected value between these two, okay, that should not change. Anyway, this is the definition. Okay. Now, you see, now come back to the physical problem. What is our purpose? I am trying to filter, derive a filter, so that this output becomes a good estimate of d n. As I told you, no point in equating y equal to d n and solve the equation with so many unknowns and only one equation, because even if you find some solution of that equation, next for the next index data changes, immediately equality goes. And since input is random, this is random, dn is random, dn minus yn en is random. So, that means you have to minimize some statistical property of en, which gives the power of en. If the en's power goes, then that means en itself becomes a low power signal, it never takes very high value. Okay. It has to be again I have to apply average, because there is no point in taking say en square, because for a particular experiment you observe one en, you try to minimize en square and you get some set of coefficients, suppose that may not do good, because next time the data changes for the next experiment, that time you get a new sequence en, for that your these coefficients are not optimal. So, that is why it has to be some average power of en, isn't it? That is called the mean square value. You understand one thing, if x n is 0 mean, y n has 0 mean, d n also I am telling 0 mean. So, d n minus y n, that also has 0 mean. So, e n has 0 mean. So, around 0 mean, how much is the average, how much is the instantaneous power? E square n. Okay. Capital E of E square n will be the expected power, average power, and because of stationarity, y n is stationary and x n and d n they are jointly stationary. So, overall E of E square n will evaluate, that will be independent of n. Okay. That also then, that is the measure, that will give you the average power of E n. I want that to go down, not a particular E square, not E square n for a particular observation, observed waveform of E n, because that will not work for the next observation. That is why you have to bring in statistics here, you have to apply E operator. So, you take the mean square error. Square means around the 0 mean deviation, that is the power, AC power you can say, and mean of that. Now, you can say that will depend on what? After all, E n depends on is d n minus y n, and y n is this summation. So, if you take the square of E n, what will happen? D n minus this entire thing, that will be squared up, then expected operation. Squared up thing will consist of terms like w 0 square, w 1 square, dot dot w p square, w 0 w 1, w 1 w 2, w 2 w 3 is a second order term in w 0 to w p, isn't it? So, it is a function of second order function of, it is a quadratic function of the filter weights. Any quadratic function has got either a unique minima or a maximum. In this case, it will be minimum. What? Mean square error. That will give you the optimal set of weights. And as I do that, that will work out expression of square error, but that will be your optimal weight. You have heard of Mawabina. Mawabina is a great communication is the father figure. Electrical computer, all of them should know that. It is he who is master CC brought in Boolean algebra to the design of CC circuit. He put the note. নমস্কার টিউটোরিয়াল introduction of Boolean the design of all these AND gate, NOR gate and all this design what was this time. Okay, this is the I don't know why meant. Anyway, so this En since I know that it will be independent of n, I am already calling it epsilon square, but we will see that it is indeed independent of n because of stationarity. Okay, what is epsilon square? Mean square error of the output error, which is a quadratic function of all the filter weights, and I want to minimize it. Okay. So, what I do, and I suggest you follow the way I teach, because some books might do in a very elaborate way and term by term differentiation and all that. Don't do that. We will do things in a smart way. This is your En, this is En, isn't it? Dn minus W transpose Xn. Please see this. W transpose Xn, we should never forget. This is the output Yn. W transpose Xn vector. W transpose Xn vector. That is your output Yn. Dn minus that. This is your En, but it is E square n. So I have to repeat it. But what I will do? I will repeat it, but it is a scalar, and these are the smart tricks I will apply. This is scalar, and scalar quantity or its transpose they are same. Okay, so I will write it as its transpose. Okay, and now you expand. There this multiply. There will be 4 terms. First one will be Dn into Dn transpose, that is Dn square itself, which does not depend on your filter weight. It is an external signal Dn, it will give the power of Dn. First term, and this is independent of filter weight. This is the power of the Dn, and if Dn is a stationary process, I am assuming Dn also to be WSS, it will be the power. Average power of Dn, you can even denote this independent of n because of stationarity of Dn, you can call it sigma d square. Minus, there is a cross term linking these two, and there is a cross term linking these two. Okay. Now, can you see that W transpose Xn into Dn, if you take, and if you take the transpose of that, you get back this other one. Say, such things you get accustomed, na? This kind of, I mean, what? W transpose this cross term, we are in the initial phase of the course, so I am doing step by step, but very often this matrix tricks and all I will apply at random. W transpose Xn into Dn, and the other cross term is Dn X transpose n transpose Wn. Okay. My claim is both are same. So, this is a scalar W transpose Xn, W transpose row vector, Xn column vector. So, scalar into scalar. Here also X transpose row vector, W column vector. So, scalar into scalar. And my claim is they are same. All are real. My claim is they are same. That is not difficult. You take this guy, the scalar and transpose. If you take the scalar or take its transpose, they should be same. But if you take the transpose of this and transpose of this. So, first transpose of this means W transpose n X n, and then D transpose n, but Dn is a scalar. So, transpose of Dn is Dn, isn't it? You can do it by elaborately expanding Xn, Wn and term by term, but do not do that. You got this idea? So, the two of the cross diagonal elements, the two cross elements actually, they are same. Are you convinced? So, that means twice I can write E plus the last term E W transpose x n and transpose of this okay. W does not come here, I have to minimize it as a function of W all the weights, but W does not come here, W comes here and here. This is where you will get the quadratic terms because two W's occur, here only one W occur. Anyway, W is a constant, I can take W transpose out and E of x n into d n. W transpose, are you getting me? W transpose into x n into d n, then E. Why not take E on x n d n and then pre-multiply W transpose? We will get the same thing. Na? You understood my logic? Suppose A transpose B and B consists of random vector, A consists of constants, E of that. One way is to multiply all the elements term by term and add and E apply, okay, but constants remain constant. So, you will see you will get the same thing if you take out A transpose and do this expectation first and then to A transpose, we will get the same thing. So, W transpose can come out here, similarly W transpose can come out here, this W can go out here. First you take out W transpose here, remaining thing on that E, x n x transpose n consists of random data, that times W. On that E operation, why not take out the W to the right hand side, just apply E on this. Is it difficult to can see? Huh? Whether we multiply first and take W, take expectation operation, or E on this part and then multiply, we will get the same thing, because W is independent, W is not random, W transpose is not random. So, that means this will give rise to twice W transpose. You remember I gave a definition, two things are given to us, R and P. R consists of the, R is the input autocorrelation matrix, P is the cross correlation vector between these. After all, you are trying to estimate d n, so you should have some kind of knowledge between d n and x n. There is a cross correlation. What kind of cross correlation they have? d n and x n. Are you following me? This vector P is suppose given to you. R is given, P is given. What is P? P is E of x n into d n. It consists of the cross correlated terms. Okay. So, you get W transpose out, E of x n into d n, that is P, E of this on this, that is your P, and W transpose comes out, W go out, E of only this part which is R. R is, we are assuming positive definite. It is always positive semi-definite, but we are also assuming positive definite, so invertible and all that. Okay. That is a full rank process, not linear relation amongst the samples of the process x n. Now, here you see W transpose P, P is a column vector, real data, all real, W transpose row vector consisting of W 0, W 1 up to W n. So, if you multiply, you get only first order terms, W 0 only, W 1 only, no second order, no W 0 square, is not it? But here odd W, first odd W is a column vector, each element will be function of W 0 up to W n, then multiplied from here. So, you will have square terms on that side, that is why it is a quadratic function. Okay. So, what I have to do? I have to now differentiate it with respect to W 0 also, W 1 also, dot 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 W n also, equate each of them to be 0, get a set of equations, solve, that will give me W 0 to W n, the optimal one. I will get a unique solution because it is a quadratic function, it has only unique minimum, maximum, all that theory you know. But instead of doing like that, again let us do things in a smart way, because we will derive some matrix results. Suppose I have a thing like this, W transpose P, you call this quantity A. I want to differentiate del A with respect to a particular weight, so W k. Now, what is W transpose P? W 0, P 0, dot 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 W k P k plus dot 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 W n P n, isn't it? So, very simply what is del A del W k? That is this P k. So, I will define a vector now, del W, this is my notation, please follow the notation. Del W is an operator, del W working on A by definition, this is a definition. What is nothing but derivative of A with respect to W0 put in the first place, derivative of A with respect to W1 put in the same, just arrange them one after another in a vector form. I am doing nothing new, I am only deriving, collecting all the derivatives, but putting it in a vector form. That is why I am giving it and then giving a compact name here, del W of A, that is A is differentiated by the W vector. Basically, this will be del A del W0, del A del W1 dot 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 del A del W n. So, obviously, what is this vector here? General case you have seen del A del W k is P k, isn't it? Del A del W k is P k. So, what is this vector? First element is P0, P0 P1 dot 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 Pn, which is nothing but P vector. So, whenever you have got a form like this, A equal to W transpose P, first order, if you take the del of A, del of that term with respect to W, you get back this vector, this fellow. Always remember this. I will be doing this kind of operations every now and then in this course for a while. So, W transpose P, this kind of first order term, if you differentiate with respect to W, you should get back P. If you differentiate with respect to P, you should get back W. Right? W transpose P and P transpose W are same. Okay. This was simple. So, remember this formula, but there is another result I have to prove. If you have a thing like W transpose R W is a scalar, row vector, matrix, column vector. Matrix column means one column, row into column, scalar. You call it B, and given that R is Hermitian. In fact, it is real, it is a real matrix. So, R is given, since we are dealing with real case, R Hermitian means basically R is just symmetric, R transpose equal to R. R meaning R I j and R j I, they are same. R 1 3, R 3 1, R 1 4, R 4 1, they are all same. This is given to us and we are evaluating this. This is a scalar, again a function of all the weights W0, W1 up to Wn. So, I can differentiate them, differentiate B with respect to each, put them in a vector form. So, that will be my del W B. Any scalar is a function of the weights W0 to Wn, and if you differentiate with respect to each of them, put them in a vector form, I say compactly that this is del W of B, which is nothing but again the same definition, del B of del W0 dot 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 del B of del W k dot 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 del B del W. Fine. This is what we have to find out. We have to find out this. So, suppose I want to find out this general guy, general real, you have to find out del B del W k, k can be 0, k can be 1 up to k can be capital N, these I have to find out. Okay. So, let us see this B fellow, let us evaluate. What is this B fellow? B, first you form this vector, okay. Then 0th element of this guy, 0th element of this vector, first element of this guy, first element of this vector, so on and so forth. That means B is W I equal to 0 to n, and then this vector R W I. So, simple, R W is a vector, that times I mean the ith element of that into W I. Okay. R W is ith element. What will be the ith element? Now, consider R W. First row of R times W will give the first element. Second row of R times W will give the second element, dot dot dot. So, ith row of R times W will give the ith element. That means, this summation remains as it is. Here ith row. So, R I j, j will vary from 0 to n and W j this much. Ith row. So, R I 0 W 0, R I 1 W 1. You see, I am scanning that row, R I 0, R I 1, R I 2 dot dot dot, so W 0 W 1. Okay, that is what I am doing. This quantity then you see, this is how B depends on all the weights including W k, and you ask me to find out this derivative. Okay. So, the way I will go about is this: first consider this outer summation. In this outer summation, I will become equal to k once, that case I will separate out, and I not equal to k, that case I will write separately. Okay. So, this I will write as and I equal to k means W k, I equal to k case separately I am writing. So, there is W k summation or I is k here or k j okay. Wherever I had I am replacing that by k. Now, you differentiate B with respect to W k. First here in this outer summation, W k never occurring, but for each W I here there is inner summation in which W k will occur only once, that time I will get R I k. So, R I k W I. Here there is something more, it is a product. So, first you differentiate with respect to W k, so you get 1, this remains as it is. So, that you write and next time you hold it as it is, differentiate this with respect to W k, you get R k k, only when W j becomes W k, you get R k k, otherwise 0. So, R k k, okay. R k k. So, R k k W k. This R k k W k, if I club here, you see this first summation, I equal to k case was missing. If I equal to k, this becomes R k k W k, but that has come here. So, these two can be clubbed and this fellow will go, this thing will go, isn't it? Here, if it is I really will become k, if I included this I equal to k case, then I would have a term R k k W k, but that has come already. So, that means I can club the two and remove this. And secondly, here in this summation, R k j, because of the Hermitian property is same as this, you can write same as R j k. And then why carry on with j, call it I or I k W I, you get the same summation, local sum, local index. R k j I am calling it R j k because R is Hermitian symmetric matrix, j k element, k j element are same. So, R j k j and j k are same. So, R j k W j, and then why call j, you again call it I or I k W I, which is same as what you get here. So, that means this will give rise to twice this summation R I k W I. In fact, let me call it instead of R I k, rather you call it R k I. I should have instead of changing here, I should have changed here R k I, that makes it better. R I k instead of that R k I. R k I W I, again R k j W j, call this j as I. So, twice R k I W I. So, look at this, what is, and I is changing from 0 to n. So, look at this now, R k 0 W 0, R k 1 W 1, that means kth row of R is scanned, R k 0, R k 1, R k 2 dot dot dot, and similarly W 0, W 1. So, that means kth row of R times W vector. So, this is nothing but what? If it is R matrix, this is the kth row times this W vector, kth row of R is W, that is what this is, that will give you del B del W k. So, if it is W 0, that means first row times this vector, that will give you derivative with respect to W 0. If it is del B del W 1, second row times this vector. So, if you put them in a vector form, this will be nothing but R times W. So, this is equal to R W. Are you getting me? So, this is twice R W rather, there is a 2 here, twice R W. Okay. Things are not so easy in the case of complex case, in the complex case. So, I have to generalize in the real. So, I could just simply think R I j and R j I, no conjugation there, because real symmetric. So, anyway, this is what you get here. So, now I want to do this equal to 0 0 dot dot 0, that is derivative with respect to W 0 0, with respect to W 1 0, with respect to W n 0, because I am trying to minimize. So, all the partial derivatives must be equal to 0. So, del W epsilon square equal to 0, you can call it 0 vector, but we have already derived this, and this is independent of W, it will go. So, this will give rise to minus 2 p W transpose p, if differentiated with respect to W will give you p, if differentiated with respect to p will give you W. So, this is 2 p and this fellow gave twice R W. So, you take 2 cancels and take p on the other side, this will give rise to that optimal filter W equal to W opt, or sometimes in some books denoted with a cap, W opt, which is nothing but R inverse P. I assumed R to be positive definite, invertible, so I can write inverse, R inverse P. This is the Wiener filter, Wiener FIR filter. So, if you want to design the filter, you must know R and P, but often you do not know R and P, because R will depend on the, R is giving the input autocorrelation matrix, that will depend on the circumstances which is generating the input. Like in the case of your this thing, equalizer, the receive signal depends on the channel property also. So, its correlation involves the channel information, and moreover R and P, their value may change, the statistics may change from time to time. So, you cannot design it once for all, that is why you have to do it adaptively. So, from here I will march towards the basic LMS algorithm in the next class. Thank you very much.